So here we are in section 2.2. We're still in chapter 2, so we're solving systems of equations, but in this section we're going to take a look at something called the Gauss-Jordan method for solving those systems of equations. Essentially what we're going to do is we're going to redo what we did in 2.1, just use a different technique for finding systems of equations. So our objectives are to define what a matrix is, to rewrite systems as matrices, an augmented matrix to be specific, and to use something called the Gauss-Jordan technique to find those solutions. Okay, so first off, what is a matrix? Well, by definition, a matrix is a rectangular array of numbers. A rectangular array, so basically just taking a system of equations and reducing it down to a bunch of numbers. It has rows and columns. Rows go left, right. It also has columns, and columns go up, down. And there are a lot of different uses for matrices. There are a lot of different ways that one can use a matrix. We are going to look at a way to use those to encode systems of equations and then solve that system of equations. The process of encoding a system of equations just requires us to strip out all the unnecessary parts and only hold on to the necessary parts. Right? So we're going to hold on to the coefficients of the variables. So that 4 and that 5 represent that 4 and that 5. The 7 for the x and the 8 for the y represent that 7 and 8 right there. We're also going to hold on to the constants that these equations have been set equal to. We're going to use this vertical line right here to represent the equal signs that we're talking about over there. And in general, what we're going to do is we're just going to take a system of equations and rewrite it in such a way that there's less information, but the same information is still there. Meaning that when I look at this, I can recognize that that column represents the x variable, that column represents the y variable, that line represents the equals, and then that column represents the constants. CON is TA and TS. Yeah, that's right. Okay. All right. Once we encode a matrix, once we write a system of equations as a matrix, then the process is to use the same techniques that we use in the row echelon method, that is adding rows together or subtracting rows, multiplying rows by non-zero elements, all that, to transform our matrix from what we started with so that it looks like this one right here, where we have the ones on the main diagonal, zeros everywhere else, and then two values over here. I used m and n over here just to represent two unknown numbers that we haven't found yet, where those are real numbers but also the solution to the system. Because if we were to take this matrix and unencode it, that first row would read 1x plus 0y equals some number m, and the second row would read 0x's plus 1y was equal to some number n. But if we get rid of the things that we don't need to write, then that just turns into x equals m and y equals n. So we're going to use a matrix technique called the Gauss-Jordan method to make this happen. All right, so let's take a look at the steps to solve this. So if you're one of those people that needs things written out step by step, and that's fine by me, here are the steps. We're going to write the equation so that the variable terms are in the same order on the left-hand side and the constants are on the right. What does that mean? Well, x is first, then y's, then if there were three variables, z's, and then w's or whatever, how many variables there are, we'd write them in order. So all the equations match the order, and constants are on that right-hand side. Okay? So I'm going to clean this up here. So step one is, if your equations don't look right, make them look right. And by right here, we mean line up your variables, x's, then y's, put your constants on the right-hand side. Step two is to rewrite it as that augmented matrix. Strip out the variables, keep the important information. Each row represents an equation. Each column represents a position in the equation. The 4 and the 7 are the x's, 5 and the 8 are the y's, and so on and so forth. All right? Step 3 and step 4 and step 5 and so on and so forth are the row operations that we're going to use to transform our starting matrix, to our finished matrix. All right? It'll make much more sense once we do an example. Okay? And then we'll just keep working through that until we get to the final matrix, and then we'll read off our solutions. So let's look at an example and see if we can make more sense of it. Now, you might have seen this one before. This is the one from right up here. Okay? So step 1, I want to make sure that my equations are written properly. That is x's, then y's, and then constants over there on the right. So that's good. Now I'm going to encode that matrix. The first row, or the first equation, is going to give me the matrix 4, 5, 10. And the second row is going to give me the matrix 7, 8, 19. So there's my matrix. Now my goal is to turn these two values right here into 1s, and to make these two values right here into 0s. Right? Now these two values right here are going to change also. I just don't have any goal as to make those necessarily something. I just want to make them into, okay? I want to let them become whatever they need to become. All right. So step 1, I'm going to make that 4 into a 1. All right. So I'm going to leave the second row alone. But I'm going to take row 1 and replace it with 1/4 row 1. And so when I multiply that first row by 1/4, that becomes a 1. That becomes 5/4, and this becomes 5/2. It will be 10/4, but it reduces down to 5/2. And now I've got my 1 where I want it. Right? Now my next step, now that I've got that to be a 1, is to make this 7 into a 0. Okay? So I'm not going to mess with the first row right now, so I'll just copy it down, 1, 5/4, 5/2. But I'm going to take row 2 and replace it with row 2 minus 7 times row 1. Do you see how multiplying the first row by 7 and then subtracting it will make that 7 into a 0? Right? So that becomes a 0. This next position over here becomes, because I'm doing row 2 minus 7 row 1, that next position, and I'm going to do my scratch work over here to the side, is going to be 8 minus 7 times 5/4. So that's going to be 8 minus 35/4. So this is 32/4 minus 35/4. So that's going to be negative 3/4. So I get a negative 3/4. Now that last position, again using the scratch work over here to the side, is going to be, what is that going to be? That's going to be 19 minus 7 times 5/2. So that's going to be 19 minus 35/2. What is that going to be? 38? Yeah, 38 halves minus 35 halves, and that's going to give me 3 halves. Okay. All right, so I've got that first column looking how I want it to look. I've got the 1 and I've got the 0 where they need to be. Now the next thing I need to do is I need to make this column right here into a 0 up top and a 1 down bottom. Okay? So I'll turn the bottom into a 1 to begin with. So I'll leave the first row alone, 1, 5/4, 5/2. But I'm going to take row 2 and replace it with negative 4/3 row 2. Okay? Because when I multiply that negative 3/4 times the negative 4/3, it'll turn it into a 1. So 0, 1, and then I've got to do 3/2 times negative 4/3. So 3's cancel and I get negative 2. Okay. I'm almost done. Last thing I need to do is I need to make this into a 0. All right. So I'll leave row 2 alone. 1, that's a 0. 0, 1, negative 2. And I'm going to take row 1 and replace it with row 1 minus 5/4 of row 2. Well, since there's a 0 in that first position, that'll stay a 1. And in the second position, that's going to turn into a 0 because 5/4 times this 1 right here, 5/4 minus 5/4 is 0. And now the other one's going to be tricky, so I'll do some scratch work over here to the side. I'm going to have 5/2 minus 5/4 times negative 2. So that's going to be 5/2 plus 5/2. So that's 10/2, but 10/2 is 5. And now I'm done. How do I know I'm done? I've got 1s on my main diagonal. I've got 0s here and here, so I've got this looking like I want to look at it. These numbers are whatever these numbers are. And now I'm looking at my solution. That first row reads 1x plus 0y's is equal to 5, or if I write that correctly, x equals 5. And then that second row reads 0x's plus 1y equals negative 2, or if I write that correctly, y equals negative 2. And there's my solution to my system. If I'm uncertain that I've done this correctly, I can always go back to the original system of equations up top there and plug it in and check. So 4x plus 5y, so 4x plus 5y is supposed to be equal to 10. So I'll go ahead and check. 4 times 5 is 20. 5 times negative 2 is negative 10. 20 minus 10 is indeed 10. I feel good about that. The other equation was 7, 8, and 19. So 7x plus 8y was supposed to be equal to 19. 7 times 5 is 35, minus 16 is indeed equal to 19. And so that's my solution to my system. This approach is called the Gauss-Jordan approach. So let's just run through it again. Okay? Step 1 was to take our matrix and rewrite it. Actually, this is technically step 2. Step 1 is to make sure that it's written correctly. That is, the variables are lined up and the constants are on the right. Step 2 was to write it as a matrix. If you want to get specific about it, this is referred to as an augmented matrix. This part over here is the augmentation part. This is the coefficient matrix. This is the constant matrix. Slamming them together like that says we are augmenting it. And then I do row operations on that matrix to get that left-hand coefficient matrix to turn into this guy down here. I just step by step by step through it until I get to where I need to be, and then I read off the solution. We're at 13 minutes. I want to do another example, but that one's a big one, and I don't want to start that one and not have enough time. So I'm going to stop this video here, come back, and I'll start a second video, and we'll do that.